Hello, everyone. Welcome to Yebo Extra Science, Yebo Tutor Live. My name is James, and we'll be going through some physics questions today. For those that managed to see some of our previous videos, we covered some part on Newton's laws. So for today, we'll continue from there and also look into some few questions on electricity. Right, so I'm sure you guys are connected and are receiving the audio clearly, and the stream is not buffering. So if that's the case, I would like you guys to also try and connect to us via Zoom. So please, for those of you that can see the link in the description of this channel, there is a link that takes you to the Zoom meeting. The whole idea is you guys need to participate. We need to get the questions from you and address those questions and discuss mainly. We need to discuss so that the questions that you guys would be having can be addressed, and that actually helps you in better understanding some of the concepts that you feel need to be addressed, and it helps even your colleagues some of the questions that they wouldn't have asked, but I mean, like when we go through them together and we explain some concepts, it actually helps your colleagues. So what we can do is there is a barcode that is showing to the right of your screen right now below the Zoom logo. That barcode, if you QR code, sorry, if you scan it, it will lead you to the Zoom meeting, and we can have you chat to us via the Zoom meeting. So would like you guys to join, please. Just either use the link or the QR code, and we can start from there. So the meeting is ready. Let's have you guys connect, and we see if we can interact with you, because the whole idea of this exercise is to have live interaction. So who do we have? Anyone connecting? Yes, Vuyani, you can also connect too. You can also connect via Zoom. The link is there on the just below the description. So please just connect to Zoom. Connect to Zoom, then we can see if this can work. Okay, so as you guys are still connecting, we're just gonna also show what we are covering for today. So I'll be showing the question on the screen shortly, and we can start. Feel free to type in your comments if you have any question and you feel we need to address something. The comment section is there for you to also type something in. But remember, we need you in the Zoom meeting. Yes. Connect also via Zoom. That will allow you to chat directly with us. Okay, so we have Fuyani online. Let's yes, Fuyani, you can unmute your mic and talk to us. Is your mic active? I can see your mic is off. So if you, yes.
Good day, everyone.
Good day, everyone.
I hope you are all
I
well.
hope you are all well
And you are all ready for
and are
the,
all ready
the class which
for
we're
the
going to have
class
today.
we're going to have today, for the tutorial which we're going to have today. Thank you.
Okay, thank you, Vianney. I hope the audio could be heard from the other side. So what we have here is a question paper. So the question paper is that's from November 2018. So we have done some few questions from this paper, and you can look into the video recordings that are on our site. So what we're going to look at today, we're going to start from the question that's showing, that's question number 4. So I'll just make sure I zoom into the question so that you guys can see. Okay, so this is question number 4. So for question number 4, don't forget what is important is you are able to take note of the instructions that are given, and also your timely answering of the questions is important. So your exam is timed, and you need to make sure that you answer the questions within the shortest possible time so that you can manage to answer all the questions that are given within your paper, and also follow the instructions as given. So for question number 4, already we have that instruction. You start on a new page. So that's a very simple instruction to follow. And the question is, learners investigate the relationship between the mass of an object and the acceleration it experiences when constant net force is applied on the object. They use their results to draw the graph below. So we can see that graph there. So on the vertical axis is 1 over a, which is 1 over the acceleration. The units are given in meter per second squared to the minus 1. And on the horizontal axis is mass in kgs. Okay, so we'll go on to the first part of that question. It simply states, says, state Newton's second law of motion in words. Newton's second law of motion in words. So how would you answer that one? Yes, I can see you guys are connected. Anyone to give us Newton's second law of motion in words? What does Newton's second law state? So Newton's second law relates force to acceleration and mass. And as you can see, this question has already given us a graph which relates acceleration to mass. And now we need to be able to quickly identify that this has a relationship to Newton's second law. So we're looking at question number 4.1. Newton second law. Okay. So what is important to note with Newton's second law is we are dealing with a resultant or net force, and we are also dealing with acceleration and mass. So whenever the resultant force acts on an object, the object will accelerate in the direction of the force. Whenever a resultant or net force acts on an object, the object tends to accelerate in the direction of the force. So Newton's second law states that the acceleration is directly proportional. So we have acceleration A directly proportional to, what would you say? The acceleration will be directly proportional to the force. Don't forget, we're talking of the net force, right? To the net force. And inversely proportional. So we're saying the acceleration will be directly proportional to the net force and inversely proportional to the mass. The acceleration is directly proportional to the net force and inversely proportional to the mass of an object. So this is Newton's second law. So you're supposed to present this in words, and the key thing there is to know the relationship between acceleration and the net force, and also the inverse proportion between the acceleration and the mass. Okay, so that's the first part. And the second part says calculate the gradient of the graph. So that's 4.2. That's 4.2. Gradient. And I'm sure you know very much this from your mathematics and from experiment. We deal with gradients every time. And generally, for any gradient, like if you are doing your mathematical equations, you have got m equals to y2 minus y1, the increase in y over the increase in x. Those are the coordinates. So if you have coordinates x1, x2, x1, y1, and x2, y2, then your gradient is given by the change in y over the change in x. So for what we have, let's go back to the question and see what we are given. So here what we have is along the y-axis, we can choose a point. Let's see which point we can use there. I think it's very easy to read a point. This point can be read easily. That point can also be read easily. So at this point, the value of y, the value of this point on the y-axis, and our second point, we'll use the point at the origin, which is 0, 0. So now we're saying our x1, y1 is the point 0, 0. And our x, I have to Okay, and our x2, y2 is the other point. What is this point? This point here, what are the coordinates of this point? Anyone who can give us the coordinates of that point? So on the x-axis, that point is 1. And on the y-axis, same point has got a value of 2. So the question says find the gradient equals to, we say it's y2 minus y1, which is 2 minus 0, over x2 minus x1, which is 1 minus 0. And that gives us a gradient of 2. Okay, so that question screen there was covering that part. So I was saying we have x1, y1, x2, y2, we have identified those points. And for our gradient, we can safely say is that value y2 minus y1 and x2 minus x1. So that gives us a gradient of 2. All right. Okay, so let's proceed and see what else the question requires. So this is a continuation. Part 4.3. This one says, hence, determine the net force applied on the object during the experiment. So what is required there is net force. And we can still relate to what we gave as the statement for Newton's second law. Right? So from the gradient, how did we calculate our gradient? We said so we want net force. So from the gradient, we can see that for our gradient, we are using the increase in y over increase in x, and on the y-axis, we have 1 over a, and on the x-axis, that's m. So basically, this is equal to 1 over ma. And what is ma? So if we remove the constant of proportionality there, we get that our force is equal to the product of mass and acceleration according to Newton's second law. So this is F net. And that's the same F net that is given by ma in this gradient. The gradient is equal to 1 over F net. So since we know gradient is 2 equals to 1 over F net, then we can rearrange this expression in terms of F net such that F net equals to 1 over 2 or 0.5. And the units there are newtons because SI units were used in the axis kgs and meter per second squared for the vertical axis. So kg, meter per second squared, is equivalent to the Newton. So that's That's F net for you. So this is basically the resultant force according to the experiment and the graphical information given. So we've determined the net force applied on the object during the experiment. The next part says, write down a conclusion for this experiment. So how would you conclude? How would you conclude? So we can see that in this case, if since the gradient is constant, it means if F net or if the net force is constant, then the acceleration is inversely proportional to the mass of an object. So we can conclude and say acceleration is inversely proportional to the mass of an object, and this is provided the net force is constant. So that can be a concluding statement in terms of what we see from the given graph. So in other words, you can also put it to say the inverse of acceleration is directly proportional to the mass of the object if the net force is kept constant. So it's all one and the same thing. So it's still acceptable to put it that way. Okay. So that's about it. That's question 4 for you. Would you guys have questions regarding to this part? If not, we could proceed. Okay, so we have question number 5. And the question is showing on the screen. It reads, a crate with a mass of 25 kgs slides down a plane, which is inclined at 15 degrees to the horizontal. During the first part of the motion from A to B, there is no friction between the crate and the plane. But part BC has a rough surface. Okay, so which means we have a rough surface between B and C, and already that introduction of a rough surface should tell you something about the motion of the crate on the surface. What do we introduce by having a rough surface. So we should introduce a force that is not present between A and B. We should introduce a force which is not present between A and B. And that force has been identified in this question where they say from A to B, there is no friction between the crate. So which means from B to C, friction is present. Okay. So 5.1 says draw a free body diagram of all the forces acting on the crate while it moves from B to C. Take note of the region in which the free body diagram is required. Is the region between B and C. So what we have is from the left of my screen that that part of the question is still showing. So we would assume we have B there, and that's the horizontal. The angle is given 15 degrees. Then we have the crate, right? And it's 25 kgs. Now we should identify which forces are acting on the crate. Which forces act on the crate? So the very first one, take note your forces, because they're acting on the crate, should touch the crate. So the force should not start from somewhere outside the crate. They should touch the crate. So we have here a gravitational force. We can call it Fg. Right? What other force is present? Which other force is present? So we have a normal. The normal is perpendicular to the surface. So let me use another color. Let's say purple. And we have a normal. And we'll label it N. And another force is still there that we can identify from this system. And which force is that? We have talked about this one, which opposes motion. And that force should be frictional force. Okay, so we have another force in that direction, and we'll call it frictional force. So those are the forces that act on the crate as it moves between points B and C, between points B and C. So don't forget, we've just shown them in terms of what the diagram has given us. So we would assume the crate is a point. So from that point, then we can now draw our forces. We said friction is a force in that direction. And what else do we have? The normal is in that direction, N. And finally, perpendicular to the horizontal is F, gravitational force. So this is the free body diagram of all forces acting on the crate. Okay, let's see what follows after doing that. So those are 3 forces, and you have can see the allocation of marks also given there. It should guide you as to how much information is required. What about 5.2? Calculate the magnitude of the acceleration of the crate while it moves from A to B. So part 5.2. Calculate the magnitude of acceleration of the crate while it moves from A to B. So how do we calculate that one? What do you think you would do to find the magnitude of the acceleration? We already have the forces there. So we'll redraw again for the sake of others. 15. So in this case, we're starting our motion from point A. Don't forget we have different points there. So what we have for this part of the question is the motion from point A to B where there is no friction. Take note, there is no friction there. So we want the magnitude of the acceleration of the crate while it moves from A to B. So with the crate at point A, 25, or let's just say mg, and there is a component perpendicular to that incline, which is the normal. And there's a component of the weight down the incline, which is the net force that brings about the acceleration. So that will be the net force bringing about the acceleration. So what is that component down the plane? What is the component of that force down the plane? So first, for us to be able to identify that component, we need to identify also the angles that we have in this setup. Okay. So what we have is a case where mg makes an angle of 90 degrees to the horizontal, and when we tilt, such that when we tilt the incline, the horizontal to the incline also shifts by the same angle by which the incline is tilted, making that angle 15 degrees. So when we deal with components, the angle that is between a component and the vector is a cos theta component, and that makes this one mg cos 15. Down the incline, we therefore have mg sine 15. Okay. So that's how we can quickly identify our components. So back to the question, we need those components to calculate the magnitude of the acceleration of the crate while it is moving from A to B. So we're saying F net is equal to MA. And in this case, this net acceleration, since there's no friction or there is no other force down the incline, say for the component mg sine 15, then we have mg sine 15 equals to the mass of the crate times the acceleration that we need to find. So it means our acceleration is equal to 9.8 times sine. So that's 9.8 times sine 15. So you can calculate this one and tell us what you get. What is that product? So if my calculator gave me a correct figure, that should be 2.54 meters per second squared. So the acceleration of the crate between points A and B is 2.54 meters per square second. Okay, I hope you guys are following and it's making sense. 5.3 says, write down the direction of the acceleration of the crate while it slows down from B to C. Right, only up the slope or down the slope. So what would you say? What would be your choice there? When the crate is now between the points B and C in that rough surface zone, what will be the acceleration and in which direction is it? So obviously you know that when the object begins to slow down, it is experiencing an acceleration in the opposite direction, which is basically deceleration. So it means we have a net force opposing the direction of motion of the object such that it decelerates. So the acceleration of the crate between B and C should be up the slope. So for 5.3, our choice should be up the slope. So that should be, from that reasoning, it's a deceleration. So it means the net force responsible for that deceleration should be in the opposite direction. Okay, 5.4. 5.4, the magnitude of the net acceleration from B to C is 1.2 meters per second squared. Calculate the magnitude of the frictional force acting on the crate. So where is our diagram? There is the diagram. Now we are between points B and C. So Okay, so we have part 5.4. And we are given that the acceleration up the slope is equal to 1.2 meters per second squared. And we need to find the magnitude of the frictional force. So let's draw the diagram. It gives us a picture of what's happening. At this point, we said we had the weight, the normal, friction, and those are the three forces we identified first. So knowing that we have a net force in the direction opposite the motion, then we can make an expression or an equation to say the components here are such that, let me take black again. We have a downward component which we called mg sine 15, and another component opposite with the normal, which is mg cos 15. So that means our expression is mg, that is parallel to the incline with mg sine 15 minus the frictional force should be equal to the acceleration times the mass, which is the net force. And so already you can identify that we have used the direction down the incline, positive direction. So the direction is positive down the slope. So the directions are very important in this case. Hence we have m25 times 9.8 minus the frictional force, we don't know, we need to find that, is equal to 25 times A is up the slope. We have identified the acceleration, so it's minus 1.2. So rearranging that and making frictional force the subject, we get 25 times 9.8 plus 25 times 1.2. The sign changes, equals to the frictional force. What would you get for your frictional force? Sorry, I omitted the sine 15 there. There should be sine 15. They should be multiplied by sine 15. So it's 25 times 9.8 times sine 15 plus 25 by 1.2. And that gives 93.41 newtons for frictional force. So that's how we get the frictional force for the crate as it decelerates between points B and C. Okay, so I hope this is clear enough. Yes, 2.54, we had viscolite commented there, frictional force, normal force, and FG. Okay, wonderful, viscolite. Thank you for those comments. I'm sure you are following and you were able to identify the three forces that act on the crate as it moves down the slope. Perfect. So let's see if we can go to the next part. So that's question number 6. So feel free to chip in, guys. If you have any comment or you feel you have a question, you have an option to type it in the chat box on the channel for this streaming, or you can call us through the Zoom platform. We have a link showing in the description. The channel description is a Zoom link that you can use to tune into our Zoom platform and we can chat from there. The other alternative is to just scan the QR code that you can see on the screen and it will automatically direct you to the same platform. So for those of you that will see the recording later, it's okay. If you would have any questions the next time you find us live and online, if you have any questions, we'll be happy to assist. So let's see this next question. Question number 6. Six point one requires you to state Newton's law of universal gravitation in words. So these definitions, you should always make sure you state them as they are. You don't alter them, and they are just free marks that you need to maximize on. So just make sure you are well versed with the definitions, with the laws, and the different principles that can be asked. So for Newton's law of universal gravitation, we have each particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of the masses. So if we can call the masses M1 and M2, then the product is M1 times M2. And inversely proportional to the square of the distance between their centers. So if that distance between centers is r, then we can say the square of r. So particles in the universe attract each other with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. So that's basically what this expression represents. And if we remove the coefficient, if we remove the proportionality constant there, we have Fg equals to our proportionality constant G, which is the universal gravitational constant, M1, M2 over R squared. So this is not in words. What I've given there is the expression that represents what I've stated in words. So if you can remember the mathematical expression, you should be able to simply express it also in words in terms of the direct proportion to the product of masses and inverse proportion to the square of the distance of separation between the centers of the objects. So that is what that part 6.1 would require you to do. Now for 6.2, calculate the mass of the probe. So for this question, the gravitational force on a probe called Curiosity on the surface of Mars is 3,338 newtons. The radius of Mars is 3,390 kilometers, and the mass of the planet is 6.39 times 10 to the 23 kgs. So how would you calculate the mass of the probe? So already you are given everything. You have the gravitational constant. It is a table given at the end of your question paper. So we have the gravitational constant 6.67 times 10 to the negative 11. Then we know the mass of the Mars is given. What else do we know? Or already know the force that acts on the object. So from the expression Fg equals to G M1 for Mars, 2 for Curiosity, the probe, and R being the distance between the centers of the two objects squared. Then we can substitute. So in this case, R becomes the radius of Mars because this probe is on the surface of the planet Mars. Okay, so this is the force, the gravitational force Fg, and the gravitational constant G, like how we have expressed there. The mass M1 for Mars, M2, the unknown mass. This is the mass of the probe that we need to identify. And R is the radius of the planet as given. So which means all quantities here, all quantities are given. We only have one unknown, which is the mass of the probe that we need to find. Okay, so Fg, we are told is 3,338. Let's see, yes, 3,338 newtons. So we have 3,338 equals to, so our G. Okay, so let me just do a small table there. Fg equals to 3,338 newtons. The gravitational constant is 6.67 times 10 to the negative 11. And we can put units there. This will be Newton meter squared per kg squared. And what else do we have? We have M for Mars, M1, which is for Mars. And this is given as 6.39 times 10 to the 23. 6.39 times 10 to the 23 kgs. What else are we given? The radius for Mars. Which is 3390 kilometers. Take note of the units given that are also important. 3390 kilometers. That means this is 3390 times 10 to the 3 meters, because we need consistency in the units. So we have to change this kilo to scientific notation, because it's also part of the number, or to standard units. Kilograms is a standard unit. We can use it as it is. That's where we only need to be careful there. Okay. So back to our equation. Fg. Fg is the gravitational force, which we said is 338, right? Will be equal to 6.67 times 10 to the negative 11. That's for G, times the mass of Mars, 6.39 times 10 to the 23, times the mass that we need to find the mass of the probe, all over r squared. 3390 times 10 to the 3. Don't forget that was kilometers squared. So with this, we should be able to find m, the mass, which is the only unknown, the mass of the probe. I'll just put a p there so that you don't confuse that with the units. So the mass of the probe is the only unknown. Okay. So calculate. I hope you guys are also calculating. It's very important to know to calculate these figures on your own and also get the correct answer. So the mass of the probe, we can rearrange that. 390 times 10 to the 3 squared multiplied by 3338. So I'm just cross multiplying, and what we had here as G and the mass of Mars will be the denominator. Yes, 6.67 times 10 to the negative 11 and 6.39 times 10 to the 23. So this is the final expression that should give us the final answer, and our answer is in kgs, the mass of the probe. So I'll do the calculation also. 3390 10 to the 3, that is all squared, multiplied by 3338, divided by 6.67, 10 to the negative 11, which is also multiplied by 6.39 times 10 to the 23. Oh, I'm getting a nice figure there, which is 900.034 kgs. So that's 900 kgs. I hope you got the same answer, guys. I hope after calculating the mass of the probe, you are coming to the same conclusion. The mass of the probe is 900 kgs. Okay, so that's one way of also dealing with that question. You could also use another route where you find the gravitational field strength and simply multiply the mass of the probe times the gravitational field strength and equate it to the force acting on the probe. So that's also another way, but it simply means you are only rearranging or doing the same thing as we have done here. 6.3, part 6.3. says calculate the weight of the probe on Earth. Wow. 6.3 says calculate the weight of the probe on Earth. So we need to find weight of probe where on Earth. We've come back from Mars. So we want that weight on Earth. What will be the weight? Weight on Earth equals to, how do you calculate that? I'm sure that should be a bonus for you guys. Weight is, we've been writing weight from our questions with the incline. There is another weight there. So that's why I'm saying it should be a bonus, because you can quickly identify that and work it very fast. So the mass, we said we have 900 kgs, and we know G on Earth is 9.8. So what will be the answer to that? 8.820 newtons. And please don't forget to give units to your answers for quantities that have units. It is a good practice to always give your answers with their units, because units, they give sense to your final answer. They make your answer complete. So don't never forget to include units in your quantities. So this is the weight of the probe on Earth, 8,820 newtons. Okay, so do you guys have any questions? Oh, sorry guys, at some point I'm just leaving this question screen showing there, so I'll just make sure that I quickly remove it so that you see what is showing on the tablet. Thank you, team, for showing that one and notifying us about that. Okay, so that's how you can use also, guys, the chat box. In the chat box, we can also see the comments that you sent to us. They are very helpful, and at times you can also help us deal with some omissions. All right. So we're going to proceed to our next question. The next question is in this part is on optics. So maybe we'll look at the optics questions in the coming weeks for the sake of those that haven't covered them. I know some of you are in grade 12 already and would want us to address this. So we're going to arrange for you guys, don't worry. We are going to arrange the sessions nicely for you. Okay, so for our final question for today, let's look at question number 9. It's another interesting one on electrostatics. Question number 9 deals with electrostatics. So with question number 9, I'll just show it to you so that it's clearer. So we're moving on to question 9. So let's go through the question first, then we can see how best we can answer that. A small isolated sphere A with a mass of 0.2 grams carrying a charge of positive 7 times 10 to the negative 9 coulombs is suspended from a horizontal surface by a string of negligible mass. A second sphere B carrying a charge of negative 8 times 10 to the minus 9 coulombs on an isolated stand attracts sphere A so that the string forms an angle of 20 degrees to the vertical. The horizontal distance between the centers of the two spheres is 3 centimeters. Refer to the diagram below. So you can see the diagram which is shown on the screen. So the first part, definition again. State Coulomb's law in words. Who would want to give us this one? It's similar. It's a follow-up to or an analogy to Newton's law that we have just discussed. So I know if you guys see these questions coming, you'll be so excited because you can just relate between them. So in this case, we're in an electric field. We're no longer in a gravitational field, but the nature of the laws with the Newton's universal law of gravitation, they have a relationship and they have an analogy. So what can you say about Coulomb's law in words? Don't forget the question says in words. Coulomb's law. Like that. Anyone who remembers Coulomb's law? Okay, I will show. Okay, good. I think you saw the question. So that question requires us to say Coulomb's law in words. And in this case, we're also relating again force to the charge and also the distance of separation. So those are the, let me say, the key points. Force related to charge and also to the distance of separation. So how do we state it? The magnitude of the electrostatic force exerted by 2-point charges. So if we have 2-point charges, Q1 and Q2, then the electrostatic force, I'll call it Fe, is directly proportional to the product of the two charges, which is Q1 times Q2, and inversely proportional to the distance of their separation squared, or to the square of their distance apart. So the electrostatic force between 2-point charges on each other is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them, like that. So when we remove the constant of when we include the constant of proportionality, we have K as the constant of proportionality multiplying Q1, Q2 over R squared, where K is given by 9.9 times 10 to the, let's see what value, 9 times 10 to the 9, okay. So it's 8.9 times 10 to, so it's 9 times 10 to the 9. So that's the value of K. And the units there will be newtons per coulomb squared, or Newton meter squared per coulomb squared. Like that. Okay. So this is Coulomb's law. And you need to state it in words as the question suggests. Right, part 9.1 is what we have just done. So let's move on to part 9.2. Part 9.2. Draw a vector diagram of the forces acting on sphere A and indicate at least one angle. Okay, so we need a vector diagram, then we need to indicate at least one angle. So for 9.2, we'll try and draw the diagram. So it's forces acting on sphere A. So that is also important. We are dealing with sphere A. Sphere A is held by a light thread, and sphere A has a mass that we have been given. So let me use different colors there. So for the thread holds sphere A through a tensional force T. Then we have a force that acts from A downwards, vertically downwards, and that's gravitational force. Let me call it Fg. And due to the attraction force between A and B, there is a force from A to our right. As you can see from the diagram, B is to the right of A, so B attracts A. So A is attracted to the right by an electrostatic force, which is in purple, and we'll call this Fe. Okay, that's the electrostatic force pulling A to the right. Then we are given that we should also express or give at least one angle. The obvious one is this one. The angle between the electrostatic force and gravity is 90. But you wouldn't also want to give an obvious one, right? So let's have a line for the horizontal there. And knowing that we have 20 degrees here, if that is 20 degrees, then this angle becomes 70 degrees. Okay, that angle becomes 70 degrees, or T makes an angle 20 degrees with the vertical. Whichever way you present it is still acceptable. So it's all up to you. Right, have we done enough for that question? Draw a vector diagram of the forces acting on sphere A, indicate at least one angle. I think we've presented 3 forces acting on A and also labeled more than one angle. So I think we've done justice to that part. So let's look at the next part, which is part 9.3. Part 9.3. Oh, sorry, I forgot about this part again. Sorry, guys. These are the angles that we are referring to. These are the angles. So we're saying we've got the electrostatic force to the right and horizontally, the gravitational force vertically downwards, and they make an angle 90 degrees to each other. And since the rope is inclined 20 degrees from the vertical, or the string is inclined 20 degrees to the vertical, due to the attraction of our charge A towards B, then that angle means that the string makes an angle of 70 degrees with an angle of 70 degrees with the horizontal. If that is 90, that is 20, it makes that angle 70, right? So this angle with the horizontal is 70 degrees. So you can present any of the angles susceptible as long as you have given the 3 forces and at least one angle. That's what the question requires. Okay, so let's move to 9.3. 9.3 says, calculate the magnitude of the electrostatic force that sphere B exerts on sphere A. So this is our diagram, and I'll put sphere B here. Okay. And we are given the distance between sphere B and sphere A. And take note, sphere A is on an isolated stand, so it doesn't lose its charge. That's why we are told the stand is isolated. That distance is 3 centimeters. And the magnitudes of the magnitudes for the charges Q1 and Q2, or QA and QB, are given. So let me just write QA equals to, because we will use these ones, plus 7 times 10 to the negative 9 coulombs. Charge B equals negative 8 times 10 to the negative 9 coulombs. So okay, so that's basically B here. And the distance of separation between the centers of the charges is 3 centimeters. And the magnitude of the charge QB is 8 nanocoulombs. That magnitude of charge A is 7, but take note, charge B is negative. That's why we have an attraction. So the force from B on A, we say it is to the right. So that is Fe. Fe is the force on A due to charge B. So now we want the magnitude of the electrostatic force that the sphere B exerts on A. So we want the magnitude of this same force Fe. The magnitude of this same force Fe. That's what the question requires us to find. So what first comes into mind when you see a setup like this? What comes into mind? So you can see from the question that initially A is suspended and is will be lying vertically, but on introducing a sphere B, A inclines at 20 degrees to the vertical towards B because of the attraction. So that attraction, we can determine that attraction, which is the electrostatic force causing the attraction, by taking components on A and equating to the electrostatic force. So let's make equations. Let's make equations. So if the system would be balanced, we can have components. Do I have different colors to use? Purple, let's see. I don't think you guys can see the green one. Let's see if yellow works. Okay, so we have a component of tension there. We have a component upwards, which is T sine 70. And the component of tension again in the horizontal towards the left is T cos 70. So the tension in the string gives us those two components that oppose the electrostatic force and the gravity. So that will help us make equations which relate to the force that we want to identify. So what can we say? If the system is balanced, then we know mg T, let me change that, T sine 70 will be equal to mg, and T cos 70 will be equal to Fe, the electrostatic force. And by dividing this t sine 70, so we have equation 1. These are two equations that we have identified from this setup. So what we're doing here is to say 1 divided by 2. Equation 1 divided by equation 2. So if we divide t sine 70 over t cos 70, we are dividing mg over fe. Now, the good thing is with this division, we can eliminate t because we still don't know t, but we know tan 70. So sine 70 over cos 70 gives us tan 70. Sine 70 over cos 70 gives us tan 70, which is mg, the mass of charge 1 we know, g we know, but fe is what we need to find, and we only have one unknown. So by cross multiplying, we have electrostatic force equals to mg over tan 70. And let's go back to find what the mass is. The mass is 0.2 grams for A small isolated sphere A with mass 0.2 grams. So that is given in grams. We need to convert to kgs, take note. And what else do we need? We just need to recall that G is 9.8. Okay, so we have 0.2 grams, which is 0.2 times 10 to the minus 3 kgs. I've converted that to kgs. So it's very important, guys. Always make sure if you are given your quantities in units other than standard units, convert first to standard units. It makes everything easier and simpler for you. So 9.8 there over tan 70. That should give you the electrostatic force. So can someone calculate that and tell us what they get? Yes, force diagram. We have a force diagram that comes to mind again. This a whole picture gives us again the same concept of the force diagram. So we have tension there, force, electrostatic force, and Fg, which is almost similar to what we identified at some point, you remember? So that was team identifying the concept of the force diagram coming into the picture from what we're dealing with. So these things are all related, guys. They are all related, which is an interesting thing. So with this, we should be able to identify what the electrostatic force is. Has anyone done the calculation? 0.2, 10 to the negative 3, multiplied by 9.8, and divide by tan 70. 7.13 times 10 to the minus 4. 1, 2, 3, 4. Yes, 7.13 times 10 to the minus 4 newtons. So this is the electrostatic force. This is the electrostatic force applied or exerted by B on A. The electrostatic force exerted by B on A. Okay, so let's do the last part, and I'm sure you guys would be getting tired by now. We need to take a break and we'll resume. Please take note, guys, tomorrow, same time, 3:45, we have, we're gonna have Fuyani come in, and he'll be taking you through the maths part for Yebo Extra Science. So you'll be live. You are free to join and share our channel with your colleagues, and also send some comments if ever you have any, and also basically like and subscribe, because this is what this is all about. And we expect you to also come in and have fun with us as we chat on Zoom and also via our chat boxes, so that we can have fun as we benefit something from the whole exercise. So let's see what our last question is about. The last question here is part 9.4. So part 9.4. Calculate the magnitude of the tension force in the string. What will be the tension in the string? So 9.4, tension in the string. Tension T. So already we have Fe. What did we say Fe is equal to? We have already an equation number 2. So from equation number 2, our tension cos theta cos 70 is equal to Fe. So T will then be equal to Fe over cos 70. And T in newtons will be the answer that we got, 7.13 10 to the negative 4 divided by cos 70. So I'm getting 2.44 times 10 to the negative 4 newtons. The tension there is 2.44 times 10 to the negative 4. Okay. So, yeah. That's about it. That's how we can find the values that are asked for in this question. So take note, the question though has not told us anything about the system being in equilibrium. That's an assumption that we have made, that the system in the diagram, in the state that the diagram is showing, is in equilibrium, such that we have balanced up the forces given. So this is an assumption that has been made in answering parts of this question. So otherwise, without that assumption, we have some variations, but basically the figures will be within the same order of magnitude. Okay. So that's it, guys. If you guys have any questions, this is the time. Otherwise, it was nice having you on the platform, and we hope you continue joining us and benefiting from this program. So this is me, James, here on Yebo Extra Science, and it was a pleasure having you, Viscolite team, participate. We would want all of you guys to also tune in next time and also be on our Zoom platform, so that we can interact and see how best you can get the assistance and get the best of what we have to offer. Otherwise, for now, it's goodbye. You guys, all the best with your studies, and stay good. For now, it's cheers.